2018, paper 1. Tricky question really, just because it's not scaffolded. It's 6 marks and a big blank page with no, it's not broken down in any way scaffolded. So, first of all, use your knowledge of structure and bonding to explain why sodium has a higher melting point than sodium iodide, and why sodium bromide has a higher melting point again. So first of all, let's pick sodium, because sodium is a metal. It's an element, so all atoms are the same. So you're just going to describe metallic bonding first of all. So sodium has metallic bonding, worth a mark, and then you've got to say what metallic bonding is. Well, it's a strong intermolecular bond between the atoms, a strong structure, because the sodium loses electrons which become delocalized, move through the metal, hence it conducting electricity, or metals conducting electricity. And the metallic bond is the strong attraction between the plus charge ions of sodium and the delocalized negative electrons throughout the metal. Incidentally, if you're asked, what about magnesium? Well, magnesium would form Mg2 plus and 2 minuses. So that would have an even higher melting point than sodium, and even stronger metallic bonds, because there'd be 2 plus charged ions attracting more delocalized electrons, and then aluminium, Al3 plus, releasing 3 electrons to be delocalized throughout the metal, would be even higher as a melting point. I know it doesn't ask that, but it could do. Delocalized is a key word. Okay, what's next then? Sodium bromide and sodium iodide. So you've got to say they're both ionic to start off with. Sodium's in group 1, wants to lose 1 electron to complete its outer shell. Br and I are both in group 7, want to gain 1 electron to complete their outer shell. So the sodium atom donates an electron to the Br or the I, so it becomes Na plus and Br minus. And it's the strong attraction. Ionic bonding is the strong attraction between the oppositely charged plus and minus ions. So in a lattice, you've got to mention that, a large ionic lattice, and it gives very strong intermolecular bonds, so strong bonds within an ionic compound. Okay, now then the comparison between the bonding. So, which it says that in the question, if you read it carefully, why sodium bromide has the highest melting point and sodium iodide has the least. Well, first of all, you've got to say that sodium bromide, the reason it has the highest melting point is that the Br atoms are smaller, certainly smaller than the I atoms. It's further up the periodic table. So you've got ionic bonding, which we know is very strong, and you've got smaller Br minus ions. They can pack closer in the ionic lattice, and the ions can get closer together and have very strong ionic bonds. Whereas the sodium iodide, iodine as an atom is a larger atom, and therefore when it forms I minus, those larger ions can't pack and get as close together in the ionic lattice, and therefore it's weaker ionic bonding in comparison to sodium bromide. Okay, what about shapes of molecules then? Let's have a look at this one, NH2 minus. So what do? First of all, we find the central atom, of which there's 1 atom, so that's the N. Find out the group number 5. If there's a minus, it means it's gained 1 electron, plus you'd take 1 off, but it's gained an electron. So instead of 5 in its outer shell, it's now got 6 in its outer shell. 2 hydrogens bond on, that leaves 4 electrons left over, 2 lone pairs. It's got 2 lone pairs and 2 bonded pairs. If I was going to draw it, I actually wouldn't draw it like that. That's been taken from the mark scheme, and I think that's a poor diagram. I would draw it as a tetrahedral structure, a bit similar to sort of methane, but I'd have N in the middle, 2 H's and 2 lone pairs then on a tetrahedral structure, either as those sort of lobes or as 2 pairs of dots. I'd put the minus charge around it in square brackets because we're not quite sure where the minus charge is. That's fine, but I'll be drawing that in a tetrahedral kind of structure. What bond angle is it, however? Well, If you had 4 bonded pairs like in methane, it'd be 109.5, and every time you replace a bonded pair with a lone pair, you subtract 2.5. So 109.5 subtract 2.5 is 107 if there were 3 bonded pairs and 1 lone pair. Subtract another 2.5, it comes down to 104.5. Now, even though you've drawn it as a tetrahedral structure, that's not how you describe it. You describe what you see, and you only see the bonding pairs, so that will be V-shaped or bent. Now, it says justify your prediction. Anytime that it says justify your prediction or mentions the word electron pair repulsion theory, that's going to justify your answer. So, what is the electron pair repulsion theory? Electron pairs repel as far apart as possible. That always gets you 1 mark. And the second mark is that lone pair repulsion is greater than lone pair bonded pair repulsion, which is greater than bonded pair repulsion. That always gets you the second mark. Always put both points down anytime you're asked to justify something around shapes of molecules, or anytime it mentions electron pair repulsion theory.